Ever felt like the internet just gets you? Like it knows exactly what movie you want to watch next.
Or maybe spots that perfect flight deal just when you were thinking about a vacation.
Exactly. Well, there's a kind of hidden intelligence at work there, and that's precisely what we're diving into today here on the Deep Dive.
Hmm.
Our mission, as always, is to cut through the noise, give you a shortcut to being well-informed. We want to pack it with surprising facts and those aha moments.
Those moments of clarity.
For this deep dive, our source material is a really foundational book, Programming Collective Intelligence by Toby Segaran. O'Reilly published it back in August 2007.
A classic in the field, really. Even though it's from '07, the core ideas are still so relevant.
Totally. We're going to unpack this fascinating world of collective intelligence. We'll look at the underlying machine learning algorithms that make it possible and reveal how data from groups of people like all of us can be used to generate novel, sometimes really surprising insights.
And this isn't just about, complex tech jargon. This deep dive, it'll reveal the surprising logic behind so many systems you interact with daily.
Like what specifically?
While the recommendations that pop up on shopping sites, the way your search results get ordered, knowing how this stuff works kind of empowers you. You start looking at information differently. It helps you move from just passively consuming stuff online to actively observing, being more informed. It's like seeing the digital world with new eyes.
Okay, let's unpack this then. At its core, what is collective intelligence?
Fundamentally, it's about combining the behavior or preferences or maybe ideas of a whole group of people.
To create something new, an insight you wouldn't get otherwise.
Exactly. Think about it. An entire group often knows more or has more diverse perspectives than any single individual. It really is a case of the whole being greater than the sum of its parts.
Right. Makes sense.
What's important to remember, though, is that collective intelligence, well, it was possible long before the internet.
Oh, yeah. How so?
Think about something as simple as a survey or a census. You collect answers from a large group. You can draw statistical conclusions that no single person would have known on their own.
Ah, okay. Like predicting election results from polling data.
Precisely. But new communication technologies, especially the internet, they just massively amplified its importance, made it a cornerstone of the digital age. But the essence remains the same, building new conclusions from independent contributors.
We see this everywhere now. Take Wikipedia, for example.
Good example.
It's this huge online encyclopedia created entirely from user contributions. It's way larger than any single coordinated group could ever create. What's interesting there, though, is Wikipedia primarily just tracks changes, right? It shows the latest version. Its collective intelligence comes from direct human input, not necessarily these clever algorithms processing data in new ways.
That's a really key distinction. Let's contrast that with, say, Google.
Okay.
While Wikipedia absolutely relies on its user base, Google extracts important information from what web creators do on their own sites.
You mean like how they link to other pages?
Exactly. They use that linking structure to rank search results. This book, and so our deep dive today, it focuses more on algorithms, like Google's PageRank, algorithms that process user data to create new information that hopefully enhances the user experience.
And that data, it can be gathered explicitly, like when a site asks you to rate a movie?
Yep. Or it can be gathered more casually, maybe implicitly,
Yeah.
just by observing what people purchase or what links they click on.
And the applications are everywhere, things that directly impact you listening right now.
Absolutely.
Dating sites use it to help people find matches faster by learning from everyone's preferences.
Companies predict airplane ticket prices by analyzing travel data, hopefully saving you money.
And businesses try to understand their customers better for more targeted advertising, which definitely shapes what you see online.
All real-life applications of collective intelligence, hard at work.
Okay, so we've talked about what collective intelligence is and why it's so powerful. But how do these smarter programs actually get their hands on all this data, the raw material for these insights?
Right, good question. This is where open web APIs come into the picture.
APIs, application programming interfaces.
Exactly. Open APIs are essentially ways companies allow programmatic access, like access for computer programs to data from their websites. They use a specified protocol.
So like standardized doorways for data?
Yeah, it's a great way to put it, yeah. This lets other programs download and process user contributions from these sites. And the book highlights how programming languages like Python make this whole process remarkably straightforward. It really opened up a world of data for analysis.
And even back in 2007, when the book came out, the source material was already showcasing major websites with these open APIs.
Yeah, it was an exciting time for that.
I remember Dell.ico.us, the social bookmarking site. It had an API where you could download links by tag or user.
Kayak, the travel site, had one for searching flights and hotels.
eBay let you query items for sale. Even sites like Hot or Not, the rating and dating platform.
Yeah, they had an API too for searching people and getting ratings.
And for fighting spam, there was Akismet using collaborative filtering. It really felt like it was democratizing access to all this user-generated info.
And if we connect this to the bigger picture,
Yeah.
the ability to harness data created by people in all sorts of ways on different sites, that's a fundamental element of creating collective intelligence.
Right, you're not stuck in one silo.
Exactly. You're no longer limited to data from just one source. You can pull it together, combine it, mash it up, and potentially discover entirely new insights. The book even recommends a site, Programmable Web, as a starting point for finding more APIs. It emphasizes that these aren't just isolated data points, they're pieces of a much larger puzzle.
Okay, so we know where the data comes from, how we can get it through APIs. But now the really exciting part. How do we actually transform that raw data into useful insights and recommendations?
Ah, yes, the algorithms.
Let's dive into that, starting with something super relatable. How do sites suggest what you might like? Movies, products, websites.
Okay, a lot of that is handled by something called collaborative filtering. The basic idea is finding people who share similar tastes to you.
So, finding your taste twins.
Pretty much. To do this, algorithms calculate similarity scores between users. One simple way is using Euclidean distance.
Okay, sounds mathematical.
It basically plots people in a kind of preference space based on things they both rated. The closer they are in this space, the more similar their preferences are assumed to be.
Simple enough. But are there downsides?
There is one main drawback. It's sensitive to what you might call grade inflation.
Grade inflation, like in school.
Sort of. Imagine one person consistently rates movies 4 or 5 stars, while another, who likes the exact same movies in the same order, tends to rate them 2 or 3 stars.
Ah, they have different scales.
Right, Euclidean distance might see them as far apart even though their relative preferences are identical. It just looks at the absolute numbers.
You know, that grade inflation problem sounds tricky. Is there a way these algorithms can actually correct for that? I'm curious how they deal with it.
Absolutely, and that's where a different measure, the Pearson correlation, comes in. It's a bit more sophisticated.
How does that work?
It specifically corrects for grade inflation. Think of it this way. Even if your raw scores are different, if you consistently rate things higher or lower than average in the same way as someone else, Pearson correlation will spot that pattern. It's looking for the linear relationship, how well your ratings track together, regardless of the absolute scale.
That's a clever way to handle it, especially with these huge, often messy real-world data sets.
Definitely.
But what if we flip the problem? Instead of finding similar users, could we find similar items?
Yes, and that leads us to item-based collaborative filtering. Instead of comparing users to users, it pre-computes similarities between items.
So it figures out that people who liked movie A also tended to like movie B.
Exactly. It builds a sort of item similarity map based on user ratings. Imagine having a table that tells you, for every movie, which other movies are most similar based on viewing patterns.
And what's the advantage of doing it that way?
The big advantage is that it's often significantly faster for large data sets, especially sparse ones.
Sparse. You mean where users haven't rated many common items?
Precisely. Like, think about social bookmarking, like Dell.ico.us back then. Users might only share a few common bookmarks. Finding similar users is hard, but finding similar items based on all user data is more feasible. In these sparse scenarios, item-based filtering can actually outperform user-based because it relies on the overall item relationships, which are denser.
Makes sense. You don't need that direct user overlap.
Right. The book uses the Movie Lens dataset, a classic benchmark with, like, 1,682 movies rated by 943 users to show this in practice.
Okay, cool. So that's recommendations. Now, let's transition to another big area, clustering. You mentioned this is unsupervised learning. What does that mean?
Right. Unsupervised learning is different from, say, classification, where you train an algorithm with labeled examples telling it, this is a cat, this is a dog.
Okay, so it has the answers beforehand.
Exactly. Clustering algorithms aren't given any right answers. Their purpose is to find natural structures or distinct groups within the data, all on their own. It's about discovering hidden patterns, seeing what inherently belongs together without being told.
So, examples. Maybe grouping blogs based on the words they use frequently. You'd expect tech blogs to cluster together, political blogs elsewhere.
Perfect example. Or maybe grouping people's stated desires on a community website into clusters. You might find a cluster interested in outdoor adventures and another focused on quiet indoor hobbies. It finds those invisible connections.
Neat. Are there specific techniques for this?
Yes, several. For data that's just yes, no, or present absent, like does this user have this bookmark? A metric called the Tanimoto coefficient is often used for distance.
Tanimoto, how does that work?
It's basically the ratio of how many features two items share compared to the total number of features either one has. So intersection over union. It's good for binary 0-1 data.
Okay. And other clustering methods?
You also have hierarchical clustering. This builds a tree-like hierarchy, often visualized as a dendrogram, showing how individual items merge into small clusters, and then those merge into bigger ones.
Like a family tree of data points?
Kind of, yeah. And then there's k-means clustering, which is very popular. Here, you decide beforehand that you want to find k clusters, a specific number. The algorithm then tries to partition the data into those k groups.
And how do we even see these clusters if the data has tons of dimensions?
Ah, good point. That's where multidimensional scaling comes in handy. It's a technique to visualize complex, high-dimensional data with hundreds of features, maybe by squishing it down into just 2 dimensions, like on a flat chart.
So we can actually look at it and see the groups.
Exactly. It makes it much easier for us humans to interpret those relationships and spot the underlying structures that would otherwise be totally invisible in all that complexity.
Now let's unpack the magic behind search engines. It really does feel like magic sometimes, but it's actually incredibly clever engineering.
Absolutely. It breaks down into a few core components.
Okay, what are they?
First, you have the crawler, sometimes called a spider or bot. Its job is to tirelessly collect documents by following links across the web. Just keeps hopping from page to page.
Gathering the raw material.
Right. Then you have the indexer. This takes all those collected documents and creates a massive, highly organized table. It maps words to the documents they appear in, and often where in the document. Think of it like the index in the back of a huge textbook, but for the entire web. The book mentions using something simple like SQLite for storing this index.
Okay, crawler, indexer. What's third?
The query engine. That's the part you interact with. It takes your search terms, looks them up incredibly quickly in that huge index, and returns a list of relevant documents. But crucially, it's a ranked list.
The ranking. That's the secret sauce, right? How does that work?
Well, initially, a lot of it was based on content metrics. Simple things, really.
Like
word frequency. How often do your search words appear on the page? Though that can sometimes bias toward longer documents just because they have more words overall.
Makes sense. What else?
Document location. Are the words in the title? Near the top of the page, it usually signals more importance.
Right.
And also word distance. Are your search terms close together on the page? If so, it might suggest a stronger connection than if they're scattered all over.
Okay, those seem intuitive. But then came the absolute game changer.
Yes, the PageRank algorithm. Famously invented by Google's founders, Larry Page and Sergey Brin.
What was the core idea there? It wasn't just about the page itself anymore, was it?
Not at all. The brilliance of PageRank is that a page's importance isn't just based on its own content. It's calculated from the importance of other pages that link to it, and also how many links those linking pages have.
So getting a link from a really important site counts for more.
Exactly. It's like a vote of confidence. And a vote from a highly respected source carries more weight. The algorithm even uses this concept called a damping factor, usually set around 0.85.
What's that for?
It represents the probability that a user, sort of randomly surfing the web, will actually click on a link on the current page versus just getting bored and jumping to a completely random new page. It prevents importance from getting too concentrated.
Wow. That really did build a kind of network of trust or authority across the web, made it navigable.
It fundamentally changed how we find relevant information online. But they didn't stop there.
What else?
Search engines also started incorporating learning from clicks, often using neural networks.
Learning from us, clicking on results.
Precisely. Every time you search for something and then click on one of the results, You're giving a subtle signal. You're saying, this result was relevant to my query.
Ah, okay.
That click strengthens the association between the query words and that specific URL within the neural network.
So the network learns which pages are good answers for which questions?
Exactly. And what's powerful is that these networks can then make surprisingly reasonable guesses, even for queries they've never seen before, based on similarity to queries they've learned from.
So they get smarter over time, adapting to how people actually search and what they find useful.
Constantly adapting and improving. The book briefly mentions technical details like backpropagation for training these networks and using activation functions like the hyperbolic tangent, or TAN, for node responses.
Okay, so we've explored finding information, getting recommendations, but what about finding the best solution to a complex problem?
Yeah, problems where there are many possibilities and you need the optimal one.
Like planning a group trip with everyone's conflicting schedules and preferences, or even something like assigning dorm rooms to students to try and make everyone as happy as possible.
Great examples. This is where we get into the concept of optimization.
Optimization, finding the best outcome.
Right. Optimization algorithms are designed to find the set of input values that minimize or sometimes maximize a specific cost function.
Cost function, what does that represent?
It represents what you want to minimize.
Yeah.
In the group travel example, the cost function might be the total price of everyone's tickets or the total waiting time at airports, maybe with penalties for really early departures that people hate.
And for the dorms?
The cost could be the number of unhappy assignments, maybe based on student preferences they submitted. The goal is always to find the input values, the flight plan, the room assignments that result in the lowest possible cost.
Okay. So how do these algorithms actually find that minimum cost? The book mentions a few approaches.
It does. It starts with the most basic, random searching.
Just guessing.
Pretty much. Make a bunch of random guesses for the solution, calculate the cost for each, and keep the best one you found. Simple, but as you can imagine, often incredibly inefficient, especially for complex problems.
Yeah, sounds like finding a needle in a haystack by just randomly poking around.
Exactly. A step up from that is hill climbing.
Hill climbing.
Yeah, you start with a random solution, then you look at its immediate neighbors, slightly different solutions. If you find a neighbor with a lower cost, you move there. And you repeat this, always moving downhill towards a better solution.
Okay, that seems more methodical. Does it work well?
It's better than random, but it has a major drawback. It often gets stuck in local minima.
Local minima. What's that?
Imagine you're trying to find the lowest point in a hilly landscape, but you're in thick fog. Hill climbing will take you to the bottom of the nearest valley.
Okay.
But that valley might just be a small dip, and there could be a much, much deeper valley, the true lowest point, the global minimum somewhere else entirely. Hill climbing has no way to get out of the first valley it finds.
Ah, it settles for good enough nearby, not necessarily the best overall.
Precisely. It lacks the bigger picture.
So how do you escape those local traps?
That's where a clever approach called simulated annealing comes in. It's inspired by metallurgy, actually.
Annealing metal. Like heating and cooling it slowly.
Exactly. The algorithm starts like hill climbing, mostly moving to better solutions. But crucially, it sometimes accepts a worse solution, one that temporarily increases the cost.
Why would it do that? Seems counterintuitive.
It does it more often early on when the temperature is high and less often later as things cool down. This randomness, this willingness to take a step backward occasionally, allows the algorithm to potentially jump out of a local minimum and explore other parts of the solution landscape.
So it can escape those small valleys and keep searching for the deeper ones.
Right. It helps explore more broadly before settling down into potentially a much better, maybe even the global minimum.
Okay, that's pretty neat. Then the book gets into something really different, inspired by biology. Genetic algorithms.
Ah, yes, this is where it gets really interesting. Genetic algorithms are directly inspired by Darwinian evolution.
Evolution. How does that apply to finding solutions?
You start with a population of random potential solutions to your problem. Not just one, but many.
Okay, a diverse set of guesses.
Then, you evaluate how fit each solution is using your cost function. The lower the cost, the fitter the solution.
Survival of the fittest.
Sort of. You then create a new generation of solutions based on the fittest ones from the current population. This involves a few key steps.
Like what?
One is elitism. You just directly copy the very best solutions over to the next generation, ensuring you don't lose progress.
Makes sense. Keep the winners.
Then there's mutation. You take some solutions and introduce small, random changes to them. like biological mutation, it creates novelty.
Okay, add some randomness.
And the really powerful part is crossover, or breeding. You take two good parent solutions and combine parts of them to create one or two new child solutions.
So, mixing and matching the good bits from successful solutions.
Exactly. Over many generations, this process of selection, mutation, and crossover tends to evolve solutions that get better and better at minimizing the cost function. It's like natural selection, but for algorithms.
Wow, that's a powerful concept.
And connecting this to the bigger picture, there's an even more advanced idea, genetic programming.
How is that different from genetic algorithms?
Genetic algorithms typically optimize the parameters or inputs for a given algorithm or function structure. Genetic programming, on the other hand, attempts to automatically build the best program or algorithm itself to solve a problem.
Wait, it evolves the actual code?
Essentially, yes.
Huh.
The individuals in the population are actual program structures, often represented as trees. The genetic operations manipulate these program trees. It's an algorithm that creates algorithms.
That sounds incredibly complex. What are the applications?
The book gives examples like automatically recreating mathematical functions just from sampled data points, or even evolving AI players for simple board games like one called Grid War mentioned in the source. The algorithm literally writes the strategy.
It's incredible.
A key thing here, though, for both genetic algorithms and programming is fostering diversity in the population.
Why is diversity important?
If all your solutions become too similar too quickly, if they get inbred, so to speak, they might all converge on the same local optimum, just like hill climbing getting stuck. You need diversity to keep exploring different parts of the solution space.
Right, prevents getting stuck in an evolutionary rut.
Exactly.
Okay, let's shift gears now. We've talked about finding things, grouping things, optimizing things. What about predicting actual numerical values, like the price of something on eBay, or maybe housing prices?
Good question.
Yeah.
That brings us to techniques like K-nearest neighbors, often just called KNN.
K-nearest neighbors, how does that work?
It's actually a very intuitive idea. To predict a value for a new item, you first find the K most similar items to it that you already have in your dataset, where you know the value.
Okay, find its closest buddies in the data.
Right. Then, you simply average the known values of those K neighbors to make your prediction for the new item.
So it's like saying you are the average of your K closest friends.
That's a great analogy, yes. The value is predicted based on the values of similar items.
Why average multiple neighbors, the K, instead of just the single closest one?
Averaging helps reduce the impact of noise or outliers. If you just use the single closest neighbor and that one happened to be an anomaly for some reason, your prediction would be way off. Averaging smooths things out, making the prediction more robust.
Makes sense. Can you improve on just a simple average?
Definitely. You can use weighted averaging. Instead of treating all K neighbors equally, you give more weight to the closer neighbors and less weight to the farther ones.
How do you calculate the weights?
There are different functions you can use, like an inverse function, weight is one distance, a subtraction function, or a Gaussian function. The idea is that closer neighbors are likely more relevant, so they should have more influence on the prediction.
Okay, that seems smarter. But what about challenges? Real-world data must be messy.
Oh, absolutely. One big challenge is dealing with heterogeneous variables.
Heterogeneous, meaning different types or scales.
Exactly. Imagine you're predicting wine prices. Your data might include bottle size in milliliters, age in years, and maybe an expert rating from 1 to 100. These are all on vastly different scales.
Right, a difference of 10 years seems much bigger than a difference of 10 milliliters. How does KNN handle that when calculating distance or similarity?
It struggles if you don't address it. The variable with the largest range, like milliliters, would dominate the distance calculation, making things seem dissimilar based mostly on size, ignoring age or rating.
So what's the fix?
Rescaling. You transform all the variables so they fall within common range, often 0 to 1. This prevents one variable from dominating purely due to its scale. The book even mentions that these scaling factors can sometimes be optimized automatically to find the best weights for each variable.
What about variables that just aren't important, like maybe the aisle number where the wine was located in the store?
That's another issue, unimportant variables. They add noise to the distance calculation and can make truly similar items appear farther apart. Sometimes feature selection or weighting, like we just discussed, potentially optimized, can help diminish their impact.
Okay. Any other pitfalls?
One more subtle one is uneven distributions. Imagine predicting book prices, but you don't have data on whether a book was bought new, used, or at a discount store.
Ah, A hidden factor influencing price.
Right. If most of your neighbors are full-price books, but the one you're predicting is discounted, a simple average prediction might be too high.
So the average doesn't tell the whole story.
Exactly. In these cases, plotting the probability distribution of the neighbors' prices can be much more informative. Instead of just one average number, you see the likelihood of different price points.
Yeah.
You might see peaks for new and used. Using libraries like Matplotlib helps visualize this.
Giving you a richer picture, the book uses predicting eBay auction prices as an example for KNN, right?
Yes, a very practical application where these issues come into play.
Okay. Moving on to advanced classification. We talked about clustering finding groups, but classification is about assigning labels, right? The book mentions kernel methods and support vector machines, or SVMs. That sounds pretty advanced.
They are quite powerful.
Mm.
Let's start with the limitation of simpler methods. Basic linear classifiers try to find just a single straight line or a flat plane in higher dimensions to separate different categories of data points.
Like drawing a line between apples and oranges on a chart.
Exactly. But what if the data isn't linearly separable? The classic example is a circle of X's completely surrounded by O's. You can't draw one straight line to neatly separate them.
Right, any line you draw will cut through both groups, but you can clearly see they are separate groups.
Precisely. This is where the kernel trick comes in, and it's a really brilliant mathematical concept.
Kernel trick. Sounds intriguing.
The idea is to mathematically map your original data points into a much higher dimensional space. It sounds complicated, but the math allows you to do this implicitly without actually calculating the coordinates in that huge space.
Okay, why map it to a higher dimension?
Because in that higher dimensional space, the data that looked tangled and inseparable might become linearly separable. Imagine lifting the X's from the center of the circle up into a third dimension. Now you can slide a flat plane between the lifted X's and the O's still on the ground.
Whoa. Okay, so the kernel trick makes inseparable data separable by changing the perspective, mathematically speaking.
That's a good way to think about it. And then support vector machines, SVMs, come in to find the best separating line, or hyperplane, in that new higher dimensional space.
What makes it the best line?
SVMs find the line that has the maximum possible margin, the greatest distance, between itself and the closest data points from each class. Those closest points are called the support vectors. They literally support the separating boundary.
So it finds the cleanest, most robust dividing line possible.
Exactly. It's trying to make the separation as unambiguous as possible. The book mentions tools like LIBSVM for implementing SVMs and stresses the importance of cross-validation to test how well your trained model generalizes to new, unseen data.
And applications. Where are SVMs used?
Oh, lots of places. The book gives examples like dating site matching, maybe using data from Hot or not to predict compatibility, or even predicting potential Facebook friends by classifying who is likely to belong in your social circle based on various features.
Very cool. Okay, one last major technique the book covers. Non-negative matrix factorization, or NMF. That sounds different. It's another unsupervised technique.
Yes, like clustering, it's unsupervised, it doesn't need pre-labeled data. Its goal is to take a matrix of numerical observations, like word counts across documents or maybe trading volumes across stocks, and break it down into two smaller matrices.
Break it down into what?
Into its fundamental component parts or underlying features or themes, and how much each original observation is made up of those components. And crucially, these components are constrained to be non-negative. All the values must be 0 or positive.
Why non-negative?
Because it often makes the components more interpretable in the real world. You're adding features together, not subtracting them.
Okay, can you give an example?
Sure. Imagine you have a matrix where rows are news articles and columns are word counts.
Mm?
NMF could potentially break this down into, say, 10 underlying themes, like sports, politics, technology, represented by characteristic words.
Right.
And another matrix showing how much each article relates to each of those 10 themes. So an article about a new smartphone might load heavily on the technology theme, but maybe also a bit on the business theme.
Ah, it decomposes the articles into their constituent topics.
Exactly. Another example from the book is analyzing stock market trading volume.
Yeah.
You could use NMF to try and break down the daily volume changes across many stocks into a set of independent underlying market events or factors that might affect groups of stocks simultaneously.
Why use volume specifically?
The book notes that volume is suitable because it's generally additive and non-negative. NMF looks for positive features being combined. Stock prices themselves can go up or down, which doesn't fit the NMF model as naturally.
Got it. So NMF is about finding those hidden additive building blocks within complex numerical data.
That's a good summary.
What's truly fascinating here, wrapping this section up, is just how all these diverse algorithms, from simple correlations all the way up to these complex evolutionary programs like genetic programming and matrix factorization, they are constantly finding structure, finding meaning in what looks like a chaotic deluge of data that, we all contribute to every day online.
They really are making sense of our collective digital footprint in remarkable ways.
Wow. Okay, what a journey. We've gone from the basic idea of collective intelligence all the way through to these really intricate algorithms that power so much of our online world.
Things like PageRank, support vector machines, genetic programming.
Right, and realizing it's all fueled by this explosion of online data made accessible at least partly through things like open APIs.
And it's really crucial to remember these aren't just, abstract academic concepts or theories locked away in computer science departments.
They're out there in the wild.
Absolutely. They are the invisible engines driving a huge amount of the digital world you interact with every single day. They're helping companies and systems extract some pretty profound insights and make powerful predictions, all based on the collective actions of millions of people, including you listening right now.
So thinking ahead, given how much new information is being generated constantly every single day, there are clearly so many more possibilities out there for collective intelligence.
The potential is still enormous.
Which leads to our final thought for you to maybe mull over. How might you start spotting the next big application of this power? Could you identify a new, valuable data set, maybe even in your own life or work, where these techniques could uncover surprising insights?
Where's the next untapped source of collective wisdom?
Keep that curiosity burning. Keep exploring these powerful ideas, and perhaps you'll be the one to spot that next big breakthrough hiding in the data.